Now, IPsec is not one single protocol. Instead, it's a very large and complex suite of protocols. There are two data plane protocols that secure the user data IP packets, namely authentication headers and encapsulating security payload. There are also multiple control plane protocols that are responsible for things like authentication, creating and managing security associations, and for negotiating cryptographic parameters. In this webinar, I will only cover one of these control plane protocols, namely the Internet Key Exchange Protocol version 2, or IKEv2 for short. This is the most recent version, and it's also the version that you will need if you want to deploy quantum-safe networks. The concept of a security association is very important in IPsec. A security association is a set of cryptographic parameters agreed upon between the two communicating IPsec gateways. This set of negotiated cryptographic parameters includes the encryption protocol, the authentication mode, the Diffie-Hellman group, the pseudo-random function that's used for deriving keys, and the integrity algorithm that's used for generating digital signatures. And I'll cover each of these concepts in more detail later on. There are typically multiple security associations within an IPsec tunnel. IKE security associations, which are shown in blue here, are bidirectional and are used for the IKEv2 control plane messages. And IPsec security associations, which are shown in green here, are unidirectional, so they usually appear in pairs, and they are used for ESP data plane messages. There are often multiple IPsec security associations for different flows of traffic and also for rekeying. The Internet Key Exchange Protocol version 2, or IKEv2, is the control plane protocol for IPsec. It is responsible for authenticating peers, for managing security associations, and for negotiating cryptographic parameters. IKEv2 runs over UDP, and because UDP is unreliable, IKEv2 implements its own reliability mechanism using things like message IDs and retransmission timers. Also, because IP fragmentation causes practical problems related to NAT, for example, IKEv2 implements its own fragmentation mechanism to deal with messages that are larger than the path MTU, and this will turn out to be important later on. IKEv2 messages always come in pairs that are called exchanges, which consist of a request that is sent by the initiator and a response that is sent by the responder. There are several exchange types. IKE SA-init and IKE auth exchanges are used to establish the initial IKE security association and the initial IPsec security association. Then create child SA exchanges are used to establish additional security associations, either for new traffic flows or for rekeying. And finally, informational exchanges are used to tear down a security association, to report error conditions, and for other types of housekeeping. There are also some other exchange types that are defined in IPsec extensions, including quantum security extensions, which we will see later on. This slide shows the format of an IKEv2 control plane packet. I won't describe each field in detail, but the important thing is that there is always a fixed IKEv2 header, which is shown at the top here, which is followed by a series of one or more IKEv2 payloads. And each payload is identified by a payload type and has its own generic header, which is shown at the bottom here. This is a list of header types that are defined in the base IKEv2 standard. There are additional header types that are defined in IKEv2 extensions, and this once again includes the new extensions for quantum secure IPsec. Now, once again, I won't discuss each header type listed here in detail right now, but we'll see several of these header types in the next couple of slides. The IKEv2 protocol always begins with an initial exchange. The initial exchange usually consists of an IKE SA-init exchange, shown at the top here, followed by an IKE auth exchange, shown at the bottom here, for a total of 4 messages. The purpose of an IPsec init exchange is to negotiate the crypto algorithms, to do a Diffie-Hellman exchange to establish the session keys, and to exchange nonsense. And all of this is for the initial IPsec security association. Then the IPauth exchange, which follows it, does several things. First, it allows the two IPsec gateways to authenticate each other using either pre-shared keys or certificates. Second, it may negotiate, optionally, the cryptographic parameters for the first IPsec security association separately. Third, it may do, optionally, another Diffie-Hellman exchange for the first IPsec security association. Fourth, it will negotiate traffic selectors which identify the flows of traffic that are protected. And fifth, it negotiates the use of optional features. So I went through them pretty quickly, but I'll show all of these steps in more detail in the next couple of slides. Here is an initial IPsec init exchange in more detail. The security association payload, which I highlighted in red here, is used to negotiate the crypto algorithms for the control plane traffic in the initial IPsec security association. The way that it works is that the initiator, which is on the left here, sends a list of proposals, and then the responder selects the proposal that he likes most. Each proposal consists of a list of transforms, where each transform describes a particular crypto algorithm. So for example, here we see that the initiator offers two options for the encryption algorithm, namely AES and triple DES. And then the responder chooses one of those options, namely AES for encryption. And it's the same for all the other crypto parameters. The key exchange, which is highlighted in red on this slide, is used to do a Diffie-Hellman exchange, which enables the two IPsec gateways to agree on a shared secret. This shared secret is combined with other things such as nonsense, identities, and other data as input to something that's called the key derivation function, which produces the various encryption keys and authentication keys that are used in IPsec. I will cover the details of how Diffie-Hellman works in one of the upcoming slides. And finally, the IPsec init exchange is used to exchange nonces. And these nonces are random numbers that are mixed into the key derivation function to prevent replay attacks. The second part of the initial exchange is the IPauth exchange, which I've shown here. Once again, I'll go through the various fields. The identification payload, highlighted in red here, is used to identify the IPsec gateway to each other. In this example, here we're using pre-shared keys. We're using IP addresses as identifiers. The authentication payload is used to authenticate the identity of the two IPsec gateways. In other words, it's used to prove that each IPsec gateway is indeed who they claim to be. In this example, I'm using pre-shared key authentication. The authentication is performed by computing a hash-based message authentication code, or HMAC for short, over several pieces of data, including the pre-shared authentication key and the identity. And then the responder verifies the HMAC code. If the verification succeeds, it proves that both IPsec speakers have the same pre-shared authentication key, and it also proves that the message was not modified in transit. Later on, I'll show you how authentication can also be done using certificates. The IPauth message may also contain notify payloads, which are used to negotiate optional features. In this example, the use of traffic flow confidentiality padding is negotiated not to be used. Here we see another round of crypto algorithm negotiations, similar to what we saw before in the IKE init message. Except in this case, we are negotiating the crypto algorithms for the data plane IPsec Security Association, as opposed to the control plane IKE Security Association that we were negotiating previously. And finally, the initiator and the responder traffic selectors are used to negotiate which flows of traffic are encrypted, which flows of traffic flow through the IPsec tunnel. And these flows are identified by specifying a protocol, an address range, and a port range. This slide describes the Diffie-Hellman exchange in more detail. The purpose of the Diffie-Hellman exchange is for the two parties, which are here called Alice and Bob, to agree on a shared secret using some public discussion. An eavesdropper, which we've called Eve here, should not be able to determine what that shared secret is, even if she can observe the entire public discussion. I'll just summarize some of the key points here without getting too lost in the weeds. The two parties, Alice and Bob, perform a series of steps that are shown in this diagram to agree on this shared secret. Now, some of these steps involve computing what's known as a modular exponentiation. For example, you'll see something like computing g to the power a modulo p. That's a modular exponentiation. These modular exponentiation operations are computationally easy to implement. Now, eavesdropper Eve is observing this public discussion, and Eve can see certain values that are public. For example, the values P and G and uppercase A and uppercase B. From those observed values, Eve could hypothetically reverse engineer the secret values, lowercase a and lowercase b, and thereby the shared secret S. And how she would do that is shown on the gray box on the right. Now, the problem for Eve is that doing this reverse engineering involves computing what is known as a modular logarithm. This is the inverse of a modular exponentiation. And computing a modular logarithm is computationally infeasible on a classical computer. And by that, I mean that for sufficiently large values of P, it would literally take millions of years on even the biggest supercomputer that we have today to perform this kind of attack. Later, we'll see that future quantum computers are known to be able to compute modular logarithms very efficiently using Shor's algorithm. And that's what makes Diffie-Hellman quantum vulnerable. Two slides ago, I described how IPsec can use pre-shared keys for authentication. IPsec also has another mechanism for doing authentication, namely certificates. Here we see an initial IKE exchange that uses certificates instead of pre-shared keys for authentication. There are three main differences to the pre-shared key authentication that we saw in the example before. First, the IKE message includes a certificate, and that certificate is used to bind a public key to an identity. Second, the identity is provided in the form of a common name instead of an IP address. And third, the authentication method is negotiated to use some flavor of digital signature algorithm. In this case, we're negotiating to use RSA instead of pre-shared keys.